Welcome, everyone. The third speaker in our seminar series is Professor Yoshua Bengio from the University of Montreal. Yoshua, of course, needs no introduction, having won the Turing Award in 2018 for deep learning, being a fellow of the Royal Society as well as the Royal Society of Canada, being a Knight of the Legion of Honors of France, and so on. Many of you might already be familiar with Yoshua's work and have cited some of his papers, perhaps, because he's the second most highly cited computer scientist in the world. I first met Yoshua many years ago when he gave a really fantastic talk in one of the extreme classification workshops I'd organized at NeurIPS, and I'm sure he'll give an even more exciting talk today. But before we get started, a quick note on logistics. So we've reserved 1.5 hours for Yoshua's talk, so there should be plenty of time for Q&A. So if you have any clarification questions or discussion questions, then please ask them in the chat. And we have two moderators today, Amit Sharma from MSR India and Rajiv Sundararajan from the Indian Institute of Science. And they will ask your questions on your behalf to Yoshua. And Yoshua said he's open to all sorts of questions, and actually he would love for you to clarify things during the talk itself and keep it interactive. So with that, over to you, Yoshua. Thank you very much for speaking to us today. Over to you.
Thank you, Manik. So today I want to share insights and kind of research direction in topics that I'm strongly enthusiastic about. For a number of years, I've been thinking about what's missing. What kind of gap is there between current AI, current machine learning, and human intelligence? And this has motivated this whole research investigation that's connected to neuroscience and cognitive neuroscience of system 2 cognition and building system 2 deep learning, which I will explain. And today I will also tell you about a particular technical approach that we're exploring for this purpose called GFlowNets for generative flow networks, something that is a fairly general neural net probabilistic modeling tool that can be used for system 2 modeling, but actually we introduced for active learning and exploring discrete spaces like graphs. So hopefully you'll find that interesting, and don't hesitate to ask for clarifications in the middle. I'll be very happy to answer. So learning theory in the 80s and 90s was developed with the idea to give us some guarantees and some insights into generalization. In other words, what happens with our trained predictor on new data. But the assumption was that the new data would come from the same distribution and that the training data would come IID, so all the examples would be independent of each other. Unfortunately, these assumptions are not realistic. Things change. Things change in the world. There are non-stationarities. Things change through space. Maybe we have data from some countries and would like our system to work in other countries. Things change because people do things in the world, and their circumstances, the state of the world changes. So the reality is that current state-of-the-art systems can generalize quite well when they train on very large amounts of data and tested on data from the same source and the same distribution. But they tend to take a big hit in performance when you confront them to new settings. So the question is, well, if we don't use this IID assumption of same distribution for different examples, we need to have alternative assumptions. Otherwise, why would there even be any kind of generalization? What would it work on a different task or a different distribution? And in trying to answer these kinds of questions, I have found it very useful to think about how humans address these questions. And well, first of all, humans do a lot better than humans. Humans do a lot better than machines when it comes to these changes in distribution. And the hypothesis that I'm exploring is that the reason why humans are doing so well is that somehow evolution has put in us what we call inductive biases in machine learning. In other words, our internal learning machinery isn't completely agnostic or generic. It embodies some preferences, some biases that make us good at some tasks. That's what the no free lunch theorem mandates. If you want to generalize better, you need some inductive biases, some kind of specialization in some sense. And so what kind of inductive biases do humans use when they're confronted with these changes in distribution? That's one kind of question. A related question is that if you think about it, when there's a change in distribution, we want the learner to be able to reuse the knowledge that it has already acquired in its training phase. And here the question is, how should that knowledge be represented so that we can reuse that knowledge in new ways, because the distribution has changed, but maybe most of the things I knew are okay, it's just that they are kind of arranged in a different way. And this is connected to another fundamental gap between machines' current state of the art in AI and humans, and that is the ability to reuse these pieces of knowledge. That's basically reasoning. So this is not something that current machine learning is really good at, and this whole thread that I'm going to talk about is very much geared at building, say, the next generation of deep learning system that can reuse knowledge, that can reason, that can face changes in distribution. So now let's have a look at what happens with humans when they're faced with novel or rare situations that they're not used to. And what happens is that, I'm going to give you an example. Let's say you've been used to driving in a car in North America, and or maybe in India, and then you move to a different country, and you know where the traffic laws are very different. So, for example, if I go to London, suddenly there's an important change in the traffic laws that says I have to drive on the left, whereas I was used to drive on the right. Everything else is pretty much the same, but unfortunately, this small change in the rules means a big change in how I should drive. And if I just follow my habit, I'm going to make an accident. So what's going on when that happens? Just project yourself in that situation. Well, you're going to be super careful, right? And you're going to be thinking all the time while you're driving in London, I have to pay attention. I have to, make sure I stay on the left, right? And if you forget about it, you might make an accident. Eventually, after practicing this, with this conscious attention, you'll get good at it. But before it becomes a habit, you have to reason, keep thinking, oh, it's on the left, so now I have to do this way and that way, and imagine how things could be in your mind in order to find solutions to this new problem. So this is what I mean by combining on the fly old pieces of knowledge in new ways. Okay, this kind of different form of cognition, when you think about things, you deliberate in your mind before you act. This is being studied a lot by cognitive scientists and psychologists. There's a beautiful book that touches on that subject very much, Thinking Fast and Slow by Daniel Kahneman. And he talks about two systems, System 1 and System 2. And I'm going to sort of abstract a little bit that and put it in a language and a context that's maybe closer to machine learning. So System 1 abilities essentially correspond to intuitive, habitual decision-making and behavior. It can occur very quickly. So when you normally drive in your usual route, you don't need to think about it. You can do very complicated maneuvers, and it just happens quickly in your mind. at an unconscious level. So if someone were to ask you, how did you do that? You might not be able to explain all the steps. And a lot of it is happening in parallel. So current deep learning is very much like that. There is knowledge about how to solve problems, but it's implicit. It's hard to get at it. That's why we have explainability issues, in machine learning. But then there's what happens when you go to London, Now, okay, so on the left, you see the picture. The person can drive and at the same time talk to someone else because their attention is not necessarily fully on the road, which might be a mistake, of course. But that's what happens. And on the other hand, if you're in this new situation, maybe the traffic flows are different, or there's something new going on, some unusual construction, you just ask the other person not to talk to you because you have to focus your thoughts on what is going on, on your driving. So this conscious processing is slower. Like you need to think things through before you act. And it's very logical. You can explain to people why you're making such and such choices. This is very close to what happened when we design things like algorithms, code, when we're planning, any kind of reasoning. The way that our mind processes information there is very sequential. The knowledge that we manipulate is explicit because we can teach someone else, or we can explain to someone else why we did that and what order and so on. So this is a capability that we would like to have in deep learning, because I think it can help us, bridge that gap. It can help those systems manipulate at a high level these semantic concepts that maybe we knew already, but are now going to be combined in new ways that give a sort of combinatorial generalization ability called systematic generalization by linguists. There's another way to think about this that makes a connection between the IID hypothesis and the knowledge that we want to keep and causality. So think about the laws of physics. They're the same here on Earth as on the moon. But if I take pictures here on Earth, they look very different from pictures on the moon. So there really is a big difference in distribution. So if I train my object classification, whatever vision system on Earth, it might take a hit when I take pictures on the moon, or vice versa, right? Would be worse. So if you think about the physics of it, so what's going on here? It's the same laws of physics, but what's different? Well, it's like the same like Newton's laws, but the conditions in which those causal dynamical mechanisms are applied are different. Right? So in a way, you can think of it like there are two things that explain the observed data. There's the causal structure, which is invariant. It's true across the universe. Let's hope. And the things that may vary from place to place, from time to time, which you can call initial conditions or the state of the world, right? So there's the state variables, and there are the which may be hidden, and there are the causal mechanisms or the dynamics in the case of physics. And in order to be able to generalize, from the Earth to the moon or whatever, we need to separate these things. We need to learn a system where the parts of our knowledge that are invariant are going to be separated from the parts that can change from one place to another, from one time to another, and so on, which is basically about the state of the world or the initial conditions in physics. So yeah, I'm going to come back to this causality question, but let me now make a connection going back to psychology and cognitive science to a theory of conscious processing that was introduced by Bernard Bars in the 90s and called the global workspace theory. And there's some variants of it called the neural workspace theory. And one crucial element of it is that you can see for yourself, you can observe your own thoughts and see that there's a bottleneck of communication in your mind. such that very few elements can go through that bottleneck, which is the content of your current working memory. But, there are very few bits of information, very few variables that you can think about at any moment. And the theory that I proposed a few years ago is that this, from a machine learning perspective, corresponds to having inference machinery or learning machinery that also have this bottleneck. And this bottleneck means that the dependencies between variables, especially the high-level variables, the kind that we think about, the dependencies are sparse. They involve very few variables. And you can see that in language. Like a sentence involves very few words, very few variables. So if I say something like, if I drop the ball, it will fall on the ground, this is quite amazing if you think about it from a machine learning perspective. I'm able to make a very precise prediction about the position of the ball from very few bits of information, like the fact that I had it in my hands and I then drop it. The fact that we can predict accurately some abstract variable, given very few other conditioning abstract variables, is something profound. It's not true in general. Like if you look at pixels in an image, you can't predict very accurately a pixel given a few other pixels. It just doesn't work. You have to look at the whole image. And so what it means is that the kinds of variables that have that property are special. They're not the kinds we get directly usually in our sensors. They are the kind that we have in our thoughts. And we can describe their relationships with graphs. So people in machine learning working on graphical models and causality have been using graphs for a long time to describe these very sparse relationships between random variables. And one way to think about this is in the figure, you see these circles correspond to variables, and you see these squares corresponding to what people call mechanisms. So how a variable influences another variable, a causal mechanism. And you also have other kinds of variables like the pink circle that is an intervention. So when I drop the ball, I'm changing something in the world. This is the kind of change in distribution inducing cause. And these are special kinds of things. They're related to action. They're related to agency when people, usually or animals, act, and that has consequences. And maybe we can plan these consequences, or we can predict the outcomes of these consequences. But they correspond to an intervention, as it's called. Okay.
Yoshua,
So yes.
Can I ask a question? So just connecting these sparse dependencies to the causality that you discussed earlier, I'm wondering if there is an unstated prior that causal mechanisms are also sparse, at least the ones that we are looking for.
That's right. That's exactly what I'm saying. So, in principle, you could imagine a causal system where the causal mechanisms are not sparse. In other words, they take, a million causes to produce one effect. But the kinds of causal mechanisms that we think about, that we express with language, they are sparse. They involve, so a verb is typically like corresponding to an action that describes a causal relation, a causal mechanism that relates a cause, like usually the subject of the verb, to an effect, which is usually the object, right? So I drop the ball. Okay, so the action of dropping is having an effect on the ball. And that's very sparse. There's basically just two arguments here, the cause and one cause and one effect. And maybe in language you can have two or three or four causes, but it's hard for us with language to express something where there would be 1,000 causes. So it means our mind is really relying on this inductive bias, on this prior of sparsity. Absolutely. Okay.
Yeah, thank you.
So I'm going to continue. So that's the sparse dependencies between abstract variables assumption. The other assumption that you can also see in language in the same kind of example is that a lot of the variables we manipulate with our mind and in language have a causal interpretation. Like, the subject verb object example that I gave with dropping, the subject is basically a cause, and the verb is a mechanism, and the or the kind of action, which is also a cause, and the object is an effect. So and language has much more of that. So for example, it's very easy in language to express counterfactuals, like what would have happened if I had acted differently. For example, I could say, if I had dropped the phone, it would have fallen on the ground. And this is interesting because it tells us that lots of the thinking that has gone in past years to understand what causality means, not just philosophically, but from a machine learning perspective, can be used here in designing these inductive biases for future AI. One of the things that's important here is that the same mechanism, so it's not just that we have the sparse graph, but also that the causal mechanisms, these boxes that relate causes and effects, they can be reused. So there's another property of the sentence here is that, previously I was talking about a ball and dropping a ball, but I can apply the word drop on a phone. So the word drop is very general. It can be applied to many kinds of subjects and object pairs. So there's this reusability that's essential for generalization as well. Another property of the kinds of variables we manipulate in our thoughts and in language is they often look discrete, so symbolic. They're, language is discrete. I mean, there are also some continuous aspects to it, but there's a lot about our thoughts and language that is discrete. So why would that be? Well, remember I said that there is this hypothesis from Bernie Bars of a bottleneck in our mind that's at the heart of the global workspace theory. So this bottleneck is not just that there are very few variables involved in each thought, but there's a bottleneck in terms of information processing, that the number of bits needed to describe those variables is small. So, one way to make the number of bits small is to make those variables discrete. So when you discretize from analog to discrete, you throw away a lot of information. It's a bottleneck, right? And we've done work in recent years that indeed suggests that this kind of throwing away of information, if it's learned with this sort of discretization seen as a constraint, actually helps to generalize better out of distribution, which is really the goal here. So where I'm getting at is we should be designing machine learning methods and inductive biases that really explain those methods that we're going to be testing in a different way, not just on a usual test set, but what we call an out of distribution test set. Or sometimes you allow to learn a little bit, so you have some sort of adaptation. So it's what's called a transfer task. Another interesting inductive bias that has to do with the action side. So going back to my dropping, that the changes in distribution that we explain with language. So I see something happening, I say a few words, a few sentences to explain it. This is a natural thing we do. Those changes in distribution, they are sparse in the sense of localized. So very few things actually change. See, if I'm able to describe the change with a single sentence, that means it's, out of the millions of things I could talk about, I chose, these words, these entities in the world that I'm saying, okay, somebody opened the floodgate and that caused, a lot of damage. So it's very localized in this big graphical model where there are lots of possible random variables I could be talking about. There's one or a handful that comes in our thought as the explanation, the cause, the intervention is localized. And one way to think about it is when we plan to do something, often, the plan end up directed at just one or a few actions that aim at changing one abstract things or very few abstract things in the world. Okay, so intentions also can be verbalized. All right, so what do we do with these things? There's another aspect of cognition that is missing in current deep learning, at least not all of it, but some standard approaches, and that's what you could call imagination. And imagination is related to this reasoning and planning that I've been talking about, because there's a problem that if you're thinking of doing an intervention or changing something in the world, or even just looking for an explanation, like the kind of sentences I've been talking about, there are many possibilities. Well, it's more than many, it's like exponentially many possibilities, many possible plans, many possible explanations. And there's no way that our brain, at least it doesn't look like our brain is going through all of them, or even a large number of them. So, the original chess playing programs, they were explicitly trying, huge numbers of possible plans and then picking the one that looked best. But that's not the way that our mind works. If you look at AlphaGo, it's closer to the way that our mind works. The way that it does it is we've trained this neural net, which is a policy that generates candidate solutions. And it's kind of intuitive. It proposes something. It's been trained with rewards to generate things that are going to end up being good. So we need these generative models as part of the machinery for reasoning and planning. Okay. So now I'm going to move to sort of the second part of my presentation, where I'm going to talk about GFlowNets. So they are generative models. So the idea was, what kind of neural nets can we design that can generate something like our thoughts, something that can be translated into English, or natural language, naturally and easily. But thoughts are a bit different from sentences. Like sentences are linear, one word after the other, because we have this communication channel that's our voice, basically. But our thoughts aren't exactly like this. They have some kind of structure. So think of it like a parse of a sentence. It has like this tree structure, or it doesn't have to be a tree, but more generally, it's a graph that relates the pieces of our thinking together. And the graph keeps being grown as we have more pieces of thought that are sequentially added and generated. And I think graphs are a good kind of data structure to represent explanations for what is going on. So if you think about a scene, you observe an image or a short video, and you're trying to come up with a sentence, but not just a sentence, like an explanation, like the logical structure that links the abstract concepts that are involved there. And in general, a good data structure for this would be a graph as well, where the nodes represent things like variables, entities, and there would be these what would be called hyper edges that link multiple edges and correspond to multiple nodes, and that correspond to different mechanisms or different types of relations. Also, these graphs should be stochastic. Like usually, it's not like there's only one explanation or one plan. There are many plausible explanations and many plausible plans. So that's why we need a generative model that can sample from those plausible explanations. So we've been thinking about neural nets that can do this kind of thing, and also that can represent knowledge in this modular way that I've been talking about. So GFlowNets. GFlowNets can be used for these things. GFlowNets were initially designed to sample graphs. Our first paper was on GFlowNets to sample graphs representing molecules, and used in active learning to search in the space of molecules that would have good properties. But more generally, they can represent distributions over compositional objects. So a graph is compositional. We can construct a graph by adding pieces, but a set is also compositional. We can add elements to the set sequentially. Everything that you can construct sequentially, and where potentially there could be several ways of obtaining the same graph or the same set or the same object. So there are potentially many orders or many ways to achieve the same thing. It's not something that current machine learning, is really good at. Also, the object should be, compositional. So, the number of possible objects could be exponentially large or infinite if there are continuous variables involved. And so the GFlowNets will learn a sampling policy. So it's a generative model, but we think of it a little bit more like an RL. So we talk of these generative models as policies, and we talk about rewards to train them. The GFlowNets also introduce another quantity called flows, which give the name to the method. Generative flow networks, that's what the GFlowNet abbreviation comes from. And these flows are also quite interesting. They correspond to implicitly summing or marginalizing over a huge number of possible outcomes. Something that is in principle intractable, but we're going to exploit machine learning to be able to do that. Okay, so my last slide was maybe a bit abstract. So let me try to express this in a very simple scenario where we want to build a graph. So we can build a graph sequentially by adding one edge at a time. So we can imagine a neural net, which is going to be the GFlowNet neural net. It maybe is also a graph neural net, so it can read a graph as input and then produce some things on the output. So what are those things? Well, we want to take a decision about which edge to add next. So we could have an output softmax, which is representing a probability distribution over all of the legal actions that could be taken to grow this graph in one of the possible ways that it can happen. And then we're gonna sample from that distribution, and that's gonna give us a new edge, so we can add it to the graph, and we do another step. So this is the sequential aspect is there, like we add one element at a time to some construction. And we're going to learn that policy, that neural net that gives a partial construction, that takes a partial construction as input and outputs an action distribution that we're going to sample from in order to move to the next step. So the way that we're going to train this is different from the usual reinforcement learning in the sense that we're not going to ask to find the sequence of action that gives you the largest reward, but rather to find all the ways that you get good rewards. So this is actually important in applications like searching in the space of molecules, where you don't want to have just a single solution. You'd like to have all of the good solutions, especially because you want a diverse set of solutions and maybe even discover new ones that you didn't know before. So mathematically, you can express this like really given a reward function that says how good is a sequence of action, or rather the result of that, which we're going to call X here. So some object that we've constructed through that sequence of actions. So if X is our object, R of X is how good it is according to some function that, say, for now is given to us. Would like to sample these objects, so to generate them with a distribution that's going to be implicit. And that distribution, we would like it to sample objects proportionally to that reward function. So equal to the reward divided by a normalizing constant. So that's something that in principle we could do using Monte Carlo Markov chain methods, for those of you who've seen that. And these methods, however, are very expensive. They will generate an object by modifying it stochastically and gradually in small steps. But it could take forever to end up with a distribution over objects that's good, depending on the type of distribution we're looking for. Whereas the GFlowNet is more like, think about like variational autoencoders or other machine learning methods, like variational methods in general, where you are going to be able, or GANs, where you are going to be able to generate in one go. Like you generate the object. Of course, there are intermediate steps to construct the object, but it's you know exactly how much computation you need. So also to make the connection to things like Monte Carlo Markov chain methods, you can think of the reward as e to the minus energy. So energy is a term we use in probabilistic modeling to mean how incompatible the elements of the object X are with each other. So energy is low when this is a good configuration. So that's like in physics, right? So low energy or like stable, desirable in some sense configurations, and the high energy configurations are kind of bad configurations where you don't want to stay too long there. So that's the connection. So that R of X is basically that P that we're looking for is like what's called in physics and machine learning the Boltzmann distribution associated with that energy. Yes.
There's a question. So usually we're used to thinking of rewards in RL. Can you give some examples of what would be rewards in a probabilistic modeling context?
Yes. So the example I used earlier of generating good molecules, where do we get our reward from? Well, maybe we have some data that we collected from previous experiments with different molecules, and we've measured some properties of interest, like does it cure the disease? Well, that's probably what we can't measure that, but we might measure proxies for that, like how well does the molecule bind to some target protein that we think might be useful, or how well does it kill a bacteria if we're looking for an antibiotic. So we have this data, let's say call them XY pair. So X is a molecule, Y is a scalar that says how good it is. So we can train another neural net that predicts Y from X. And we can use the output of that neural net as our reward function. The advantage of that neural net is it allows to train our generative model in ways that allow the generative model to query the reward function in places like X's molecules that are not in the data, right? So basically, we're using this proxy neural net as a way to compile the information we have from the data and allow to make generalizations far from it. The problem with the predictor alone is that it doesn't tell us which molecules are good. It tells us, given a candidate molecule, how good is it? But it doesn't tell us, where to find those good molecules. So there still is a search problem. So the policy we're trying to learn here is to find all the good molecules. And so it's a generative policy that we want it to pick things that have a high, reward, that correspond to good molecules according to our trained model. So this is one example. This is what we had in our first GFlowNet paper that came out of NeurIPS. Okay. Yeah.
Clarification question. So
yeah, sure.
These small, when you talk about small volume and trying to model them, so those refer to the sparse connections that you were attempting to model earlier.
So the graphs are sparse. So yeah, the connection is not, those graphs that we're constructing are pretty small and pretty sparse. So we've been developing the GFlowNets in the first few papers to do this kind of search in the space of graphs. But where I'm going with my research program is where the graphs now correspond to things like explanations corresponding to possible thoughts we could have about some input, about a scene or something like this. But it's the same kind of object. It's a sparse graph. Could be also a sparse causal graph where there's a causal semantic to the edges.
Sure.
Okay. I'm gonna skip that. So this was the first paper that I just mentioned at NeurIPS. And there's one important keyword here, diverse candidate generation. So explanations for things in the world are diverse. There are many things you could say, and some of them may even be contradictory. So they're ambiguous. There's ambiguity about explanations. So that's why you want to have a generative model that can find all these modes, all the good explanations. In chemistry or biology, this diversity is important for other reasons, because we might not be, our proxy, our reward function is imperfect. It's not the actual, clinical trial. And so if we had 10 very different from each other, 10 solutions very different from each other, that would be much better before we try them on mice or humans, because maybe some of them are not going to work, even though the reward function said they would be okay, because our reward function is not the real thing. It's a proxy. It's an approximation of the thing we really care about. And so we want these diversity for that reason here. So we wrote a bunch of other papers. There's for people that are more mathematically inclined, there's this paper that came out last November on the mathematical foundations of GFlowNets. I'm not going to have really the time to go into the details of how this works, but we propose new training objectives for these GFlowNets that are different from the usual like RL objectives or the usual probabilistic modeling objectives like maximum likelihood. They're the closest thing in that exists to GFlowNets are what's called hierarchical variational inference. But I'm just placing that for people who want to dig deeper. I talked about already diversity. So if for people who are familiar with reinforcement learning, RL, so what are the differences? Well, you can think of GFlowNets as a particular kind of reinforcement learning method where instead of trying to maximize rewards or maximize the sum of rewards, we're trying to sample solutions with a probability proportional to the reward. That's really the main difference. And it's not a completely new idea. So there's a whole branch of RL methods, in particular based on entropy regularization. And there's also an approach called controls inference that have a similar flavor, but there are technical differences, especially when there are many ways to achieve the same objects that we want to generate. Then the GFlowNets would behave differently and I think more appropriately. We also had a more recent paper on improved ways of training the GFlowNets, and this is ongoing work because this is kind of a new territory that we're exploring as we go. We've also been exploring and how to learn that reward function. So in our first papers, what we did was we separately trained that reward function that I was talking about. Like we have data and we train in a supervised way, and then we use that as a reward function. And there's some variations there, like we could use epistemic uncertainty approximation, which is important in active learning, but basically it was a separate thing. More recently, we're thinking of how to train both the generator, which is the GFlowNet, and the energy function that which corresponds to the reward that it's trained on, given some data. So this is the first paper that does this kind of thing. And more recently, we've been thinking about how we can use GFlowNets. So now we're getting closer to the system 2 stuff I started with. How we can use GFlowNets to learn causal graphs and causal models more generally. So you can think of a causal model, like if you look on the right-hand side, is describing three things. There's the causal graph, which is how different variables are related to each other and what causal mechanisms exist that relate them. But you also have something that's important, especially if you think about agents in the world and the fact that there are changes in this region. You need to learn about how actions or interventions can change that causal graph. And then you also need to learn how these abstract variables may be related to things you can observe, like pixels in images. Right? So this is the outcomes of, if you think about experiments, we do things, we design an experiment, we run the experiment. What explains what's going on in the experiment is, in this causal graph, but then we make some measurements, like maybe we have images of cells or something, and these are outcomes. So we need to model these three pieces. The problem is there's a lot of theory that tells us that it's essentially impossible to find the model, the causal graph that explains the data in general. This is called the identifiability problem in causal in causality. And the approach that we are taking in my group is to say, okay, so even with infinite data, there will be some ambiguity about what is the right model. That's the identifiability issue. But in any case, there will be ambiguity because we have finite data. So in order to be able to plan actions properly, an agent will need to know about that ambiguity, to know about the fact that there are multiple explanations that are consistent with the data that I have observed. And we know humans do that. This is called metacognition in psychology. Humans have a knowledge of their own uncertainty. I mean, once you kind of push the ego away, you can have a sense of how much truth there is in some statement that, some thought that comes to you. And we need something like this in machine learning as well. It's a really important element of taking the right actions and planning to acquire information, for example. So in science and experimental design, we often need to decide, what are we going to do next in order to acquire as much new information as possible. And children do that all the time when they play, for example. They're curious. So in order for this curiosity to be kind of embedded in a machine learning system, the agent needs to have a sense of what it knows and what it doesn't know, so that it can go to the places to do the experiments that are going to teach it something new. And for that, what we're proposing is that we don't just learn a causal graph or a probabilistic model. We learn a distribution over causal graphs and probabilistic model that captures all of these possibilities. And that's the Bayesian posterior, right? So if you think just about the graph part, we don't want a graph. We want a generative model that samples graphs from the posterior. And remember, this is what the GFlowNets are about. They're like distributions over graphs. So we started working on this kind of idea. Yeah, as I said, this is really important in experimental design, or if you're trying to think about how children decide, where to play, what to do, and curiosity. So, so we wrote this paper that's like the first step in that direction to use GFlowNets to sample causal graphs, if you want the structure of a graphical model, from approximately, of course, the Bayesian posterior. So the Bayesian posterior mathematically turns out to be the object that contains all of the information you could potentially extract from data. Now, if you had asked me a few years ago about doing this sort of thing, I would have said, oh, forget about Bayesian posterior. It's intractable. Like, it's well known that it's intractable. We should do something different. But I now think that we have tools with GFlowNets and other methods to approximate these Bayesian posteriors efficiently using training machinery that's very close to what we currently do with neural nets and stochastic gradient descent and all that, and RL. Just as a technical peek as to how could a GFlowNet be trained to sample from the Bayesian posterior, I show this equation. So R here is the reward that we're going to use to train the GFlowNet. So the GFlowNet is actually going to sample two things. It's going to sample the model choice, theta. So think of the parameters of the energy function. And it's going to sample the latent variables z, given some data that it observes x. Okay, so x is maybe some outcomes, something we observe. Z is an explanation. So it's the values of the causal variables as well as the graph that is the explanation for that. And theta is the parameters of the causal mechanisms that we're trying to learn. Right. So we could define that reward as shown on the right-hand side of the equation in terms of energy functions that we're going to learn, because we're going to learn theta. Actually, we're going to learn distribution over theta. It turns out that if you maximize that reward, I mean, yeah, not maximize. If you use that reward to train the GFlowNet, so it's not maximizing, it's sampling z and theta proportionally to the reward, then you will get the right thing. You will get the Bayesian posterior. So I will, okay, so I guess maybe one last thing, because I did talk about this at the beginning. and that is the modularity aspect. So how can we use GFlowNets in a way that decomposes knowledge into these pieces? So for many years now in my group, we've been exploring using attention mechanisms, modular neural nets, where the attention mechanism is used to select which module should be activated at any moment. And this was very much inspired by the global workspace theory that I've been talking about. And we found that these modular neural nets trained with soft attention actually generalize better out of distribution, because they can decide on the fly which piece of knowledge to use and combine, and how to combine them, and so on. But there is still like an issue. They were trained in this usual like supervised way, essentially, and using soft attention, which mixes all the outputs of different modules in a soft way, which is very convenient for training with backprop. What GFlowNets, open is the possibility of training these kinds of modular neural nets in a way that's more like the way we think. So if you think about your thoughts, your thought, any moment, a thought you have in your mind is not a mix of 10 different thoughts. It's actually one thought. It's very crisp. That's why we have these discrete things. And so we need to incorporate, in our neural nets, not only that they're modular, but also that they take these stochastic discrete decisions. So stochastic because for the same scene you see, you might have a different thought. There's a bit of randomness there, apparently. And discrete because you pick these modules and pick these variables, and that's it. It's a hard choice. It's a random hard choice, but it's a hard choice. And GFlowNets allow us to train these kinds of modular neural nets, where the modules decide what mechanism should be used, what abstract entity should relate those, like what is the cause, what is an effect, and how to connect those into a graph that corresponds to maybe an explanation or a plan. Okay, there is a.
Sorry to interrupt.
I'm almost finished, but go ahead. Yeah.
No, go ahead. That's all. Yeah, go ahead now.
Okay, so I wrote a tutorial on GFlowNets that I'll share the link later, that people can have a look at, and all the papers are listed there. And so I'm happy to answer questions now.
Thank you so much, Yoshua, for a very thought-provoking talk. So Amit and Rajiv, would you like to take questions? And maybe it would be good if you could also read out the name of the person who's asked the question when you ask it on their behalf.
Yes, yeah, we can start with the questions. So with some of the questions, I think there's anonymous questions as well. The first question is about the sparse dependency assumption that you talked about. So the question is it only seen in language modeling, or can it also be seen in vision and other domains? Excellent
question. So I think it's seen everywhere and every modality as soon as you go to the abstract levels of representation. So when you see an image, of course, you don't have sparsity at the low level. As I said, pixels are not related to each other in sparse ways. But the abstract interpretation of the image, think about the scene parse, as people in vision have been trying to do. That's sparse. So these semantic parsing at a high level. So it's actually the kind of thing you would also verbalize. So it is connected to language, but any modality we have at the conscious level, we can translate our understanding of what we see or hear into words. I mean, it's not completely true what I'm saying. Sometimes we have a hard time doing it, but for the most part, we have that ability.
Makes sense. Another question, which I think is related to this sort of broad overview that you gave about how people think, is from Deepak Subramani. They are asking, how do we know that the brain does not do exhaustive search, but instead generates good candidates? What if it's doing something else?
Right. Well, clearly it's not doing it at the conscious level. okay, because we would know.
Yeah.
Of course, nobody knows if, under the hood, you may have this zillions of things happening in parallel for searching different solutions. But everything we know about the organization of computation in the brain, from neuroscience, doesn't point in that direction. First of all, like different areas in the brain correspond to different specializations. So the brain is highly modular. So this modularity is not just, the global workspace theory, but it's basically neuroscience. If this is known now for like many, many decades. If you peak in one place in your cortex, you will see that it's specialized to some particular kind of concepts and tasks and so on. You peak in a different places, it's a different kind. So there's this really strong modularity and specialization going on, which doesn't seem compatible with this idea that we have, zillions of replications of searching for candidates. But of course, I can't rule it out. We don't fully understand the brain.
Yeah, and I think that's probably a question for a neuroscientist as well. Moving more towards the graphical models and causal discovery that you talked about. So there are two questions. I'll maybe start with the first one, which is more general. So Anil Murthy asks, how do you see the graphical models or the Bayesian networks in machine learning evolving to perceive concepts in domains like language or vision, where there's not a one-to-one mapping between the inputs and the the higher level concepts that we might want to discover?
Right. So, I mean, let me first say something important. Usually, a lot of the work in graphical models have been focused on the graphical model itself. For example, each node maybe has a conditional distribution given its parents or something, and then we want to learn these conditional distributions. That's good, but the sort of machinery that I'm proposing here is different. So we have that knowledge about the world is still going to be represented in these mechanisms, but there are a number of differences. One of them is these GFlowNets. Well, they're not the graphical model. What they are is the inference machinery that guesses latent variables in the graphical model, or even guesses the structure of the graphical model, or in the case of the Bayesian posterior, or guesses how to combine these mechanisms to form a graphical model on the fly, because that's one thing we do when we form an explanation. So it's not like there's a static graph that explains everything. Instead, depending on the input, we're going to come up with an explanation, and at each time it's going to be a different graph. So we need to be able, so there's a latent variable here, which is the graph itself that's on the fly generated by combining pieces of knowledge you already know. So it's, okay, so having put that, let me try to answer the question. When you read a sentence, so there is the sequence of words, but that's not the complete story to really make sense of that sentence. You want to build that graph, which is an explanation. Maybe think of it like a semantic parse. So of course, there's the grammatical aspect, but if you know about NLP, there's a thing called semantic role labeling. So it's not just what is the subject, the verb, the object, but also what are the roles that different words play with respect to more abstract concepts that are implicitly given in the sentence. So this sort of graph, I mean, and I'm not saying this is exactly what is going on in our mind, but it's more like that is something we need machinery to make inference over at the time when you read the sentence, and potentially in the other direction at the time when you generate the sentence. You start with the thought, which is the abstract representation of that meaning, and then generate the sentence. So I hope I have answered a bit, but don't hesitate to ask clarifications.
Yeah, maybe I think I can ask a follow-up. So if you think about supervised ML in general on images or vision, because the causal graph is not on the input space, there often is a trade-off between the interpretability of the abstract concepts you've learned with the actual accuracy that you get. And it turns out that if you want to optimize just generalizability, you might as well not use the graph.
Yeah.
So I'm curious if you mentioned that GFlowNets can give us explanations. I'm just curious, like if GFlowNets can solve some of this trade-off.
Well, that's the goal. I don't have like a paper to give you where we do that, but that's exactly one of the motivations. So let me elaborate on that. The one problem we have with current neural nets, current deep learning, current machine learning mostly is that all of the knowledge about the world that are embodied in these trained systems comes from the data. I mean, and there's a bit of inductive bias in the design of the architecture, but most of the bits of information are coming from the data, and it's learned in a system one way. So you got this huge blob of computation, which is like these large neural nets. It's impossible, to come up with an explanation. Now let's contrast with where I want to go with GFlowNets and system 2 computation. So we still, in our brain and in the systems of the future that I'm envisioning, we still have a system 1 part, okay, which is hard to explain. But the important thing is, think of it like we have an encoder that maybe a system 1 that's hard to explain, system 1 piece of neural net. The encoder maps the low-level stuff to an abstract space, the latent variables I've been talking about. The abstract space is like words and entities that we think about.
Yeah.
And that's where the graphs are sitting. So it's like humans. When you ask humans an explanation, they are able to give the abstract explanation, the high-level explanation. They can't give you the details, the parts that they are hard to formalize, because it's not even possible to formalize in a compact way that information. So you can see an image, you can come up with an explanation for it in natural language or in your thoughts, but it doesn't say everything. Like, there are lots of details that are not there. And for many decades before deep learning became the thing in computer vision, what people were trying to do is to come up with explainable models where, based on how we think we see, based on our, knowledge of, human vision, based on our intuitions that are at the verbal level, based on mathematics, people came up with all kinds of handcrafted systems that were explainable, but didn't work that great. And part of the reason is that there's a lot in the world that simply is not reducible to a linguistic form, something you can compactly express in language or in these small graphs. So we need both. And hopefully at the end of the day, we'll have the kind of explainability that humans can deliver. Humans cannot explain everything, but they can explain sort of the tip of the iceberg, which are these abstract thoughts, abstract concepts and how they're related.
Makes sense. Thanks. And maybe I'll ask just one more question before handing it over to Professor Rajiv. So this question is from Dipen Morwani. Continuing on the causal discovery theme, is there a way to verify if the causal graph generated using GFlowNet has a causal interpretation? And would we need interventional data to do that?
Right. Well, you will probably need interventional data to learn the graph anyways. So, there's lots of theory that says that you can't go very far with pure observations. I mean, people have cooked up special distributions where you can do it, but in general, it's not feasible. Now, the question about, how do we know that we have a good model, a good distribution of our graphs? That's a great question. It's actually difficult. The best kind of solution that we're developing in my group is to use out of distribution interventions. Okay, so let's say that you have trained your system with some set of interventions, and maybe zero if it's purely observational, but as I said, it's probably not a good idea. And now you're going to put it in a new setting where maybe you observe the effect of an intervention. Maybe you know what the intervention is, or maybe you don't. If you don't, then you have to infer it. That's fine. You have inference machinery for that. And then the system is going to come up with these explanations, and these explanations can be turned into predictions of things that you expect to see. Okay, so there's the abstract level, but remember I said we also need to learn a mapping, which is like if you want a function or a conditional distribution that relates these abstract variables to the sort of thing you can observe in the real world, right? So sometimes you can observe the latent variables themselves. Sometimes you can only observe things that, whatever, images or something. So now we have to learn also that kind of model, because that basically says the model is now going to make a prediction about the sort of thing you expect to see. And now we can just test the system in the usual way, like how good are the predictions in this new setting?
Right.
So this is an indirect way of saying, of seeing how good these models are. There are other ways, for example, that relate more to humans. Hopefully these graphs are related to natural language, as I've been saying. I mean, the natural language serves as an inspiration for a lot of the inductive biases for these graphs. So we have lots of data, for example, images and captions, where the sort of low-level stuff is related to natural language. So we could use that data to learn a mapping, maybe it's stochastic distribution, that relates the abstract variables of the model, like these graphs, with sentences in natural language. So now, when we come up with an explanation, we can also like verbalize it in natural language because we have that mapping. And hopefully that mapping is simple, like, words in natural language correspond to nodes in the graph and things like that. So with something like this, now we can kind of peek into the mind of the machine in a way that makes sense, because it relates these nodes and graphs are things that correspond to words that we can, spit out a sentence, and the nodes have an interpretation, like concepts that we have labels for. So that's another way, if you want, that's more qualitative, but I think people will want to have something like this.
Thank you.
Oh, there's another thing which is related to the Bayesian posterior aspect of it. Like, how good is your appreciation of the different interpretations, like the different causal graphs, that can also be estimated. So there's a whole track in machine learning of research in what's called epistemic uncertainty estimation, which is how much ambiguity does the model have about the things it knows. And it's like, think of it like, instead of predicting the mean, you want to predict the variance, okay? It's how good are you at predicting your own errors? So this is also something we can quantify. Like, we can see, so the Bayesian posterior can be used to predict how much error you will make in your own predictions. And then you can check how well does it fit the errors. Okay, I'm sort of caricaturing, but that's another thing you could do.
Yeah, so just to paraphrase, it's not just about a particular graph that you want to evaluate. You actually want to evaluate a distribution over graphs, which conveys your uncertainty.
Exactly,
right?
exactly. Yeah. Because this is the only thing that makes sense to me. So it's very important. Like, if I only come with one graph, and maybe it's the wrong graph because there are a bunch of other graphs that are compatible with the data. And if I take a decision in the real world based on this wrong causal interpretation, we know this can be catastrophic. I mean, that's why people in causality are so like insisting that we should have identifiability. But I think it's asking too much. We in practice, like, even for humans, there are things we can't be completely sure of. Like, we can't intervene on stars, so we have to do with observational data about stars. And but we also can test our physical theories based on things we can do on the Earth. So we have a sort of generalization here. So we're not completely sure that our theories about like how stars work are correct, but we have a pretty good confidence, even though we mathematically, like, we don't have a proof because we can't do the required interventions.
Sure. Maybe I'll go with the next question. So there's a question about, is it appropriate to think about applying GFlowNets for, say, face recognition If that is the case, then what are the kinds of nodes, graphs that we should be thinking about? But maybe the larger question is.
Wait. I didn't understand the word you said. You said safe face?
Face recognition.
Oh, face recognition. Yes. Yeah.
So how do I go about thinking about a graph with nodes and so on if I want to model the face recognition problem using GFlowNets? But I think the larger question that came up again repetitively is how do I construct the graph for a given problem, or what is and how do I keep adapting it and so on?
Right. Okay. So first of all, my whole talk is about higher level cognition. Face recognition, I wouldn't put in that category. It's a very simple object recognition task that the system one, the current machine learning is very good at. We don't need to think when we recognize faces. It's instantaneous. It takes 200 milliseconds. So what I've been talking about is more like maybe if you have a scene with multiple people and there is a scenario that's going on and you're trying to understand that scenario. Okay, so that's for answering about the face recognition. So people in computer vision already started thinking along those lines. There's a whole area of computer vision called object-centric computer vision, where, okay, we have the usual coordinates, but then on top, we have some kind of graphs that explain the relationships between the objects. So that's where GFlowNets and System 2 machine learning that I talked about makes sense. Now, you asked about how do we construct a graph and adapt it? Well, we don't. It's the machine, it's a GFlowNet that does it, right? So the GFlowNet is a generative model for graphs and other discrete entities like this. So we don't manipulate the graph ourselves. We have code that produces the graph. And the code has parameters. It's a neural net. It's a neural net that constructs a graph one step at a time. So we don't need to worry about this. We don't need to design the graph. What we can design may be constraints on the graph. For example, we could decide that the graph should be sparse. So we can put some regularization that enforces that. Or we could decide that the graph is directed. For example, a causal graph is directed. So there are things we can put in the way that the graph is constructed that's going to satisfy these a priori, these inductive biases. But we don't need to design it to design the graph node per node. Or that's the point is to avoid doing that and have machine learning do it for us.
Sure. So I think this is also a related question. This is related to what you also just said. You have system 1 and system 2 learning. Is there some way for the two to interact or coexist and one feeds into the other and so on?
Yeah, thanks for the question. It's a very important question. They have to interact and feed to each other and help each other. I mean, in humans, they're intimately related. So let me try to elaborate how they are connected. So I already gave an example that maybe with computer vision, the system 1 part would be like the encoder that extracts the objects, where they are, what their attributes are. And then the system 2 models how they're related to each other. So you can make inferences, guess things that are missing, make predictions, what's going to happen next, all these sort of things at the abstract level. Okay, so that's one simple way they can interact, but there are much more like interesting ways. For example, remember my example with driving in London. Okay, so in your habitual driving, where in your usual place, it's all system 1. You've been trained to drive in those places. You don't need to think about it. You can listen to the radio. You can have you can think about solving equations in your mind while you're driving. Now, system 2 comes when I said you go to a different place. You have new traffic laws, so new instructions. The machine should now behave in a different way, and we can specify that in natural language actually, because it's abstract. So natural language is already sitting at the top. And what is going on is, of course, we still have the system 2 encoder that extracts images and so on. But now there's something going back to system 1. So now system 1 has both the vision part, but also the motor part, like how you control the wheel and when you press on the gas and all that. It's not something you have a lot of conscious understanding of. Like, it's hard to tell somebody who doesn't know how to drive how to do it. they have to practice it. There's no way you can learn how to drive if you don't practice, right? So it's system one. Everything that you can only learn through practice is system one. Things you can learn in one shot because somebody tells you you have to drive on the left. That's it, one sentence, okay? That's system two. But then you see there's a feedback, because after I practice driving in London with my system two that tells me all the time, be careful, stay on the left, it will become like a habit, and I'll be able to drive in London. It's going to take some time, but not so much time. In fact, humans are much, much better than machines at this like fast adaptation. So how does it happen? Well, so first of all, when the system one sort of motor control, you have the urge, the impulse to go to the right, but it's the wrong thing. The system two says no, it inhibits these things. I mean, it happens to us all the time. We have an impulse to do something, but like our consciousness tells us don't do that. There's going to be negative consequences, and we inhibit these actions. And if we do that often enough, eventually it's like we're training the system one motor control to do the right thing. And so now you see system two is a teacher for system one, right? So system one is a preprocessor for system two. It's also embodying like low-level policies, but system two is a guide and teacher, and it can put things in perspective that can train system one. You can also do that in your mind, so that's even more powerful. So maybe you don't even need to drive in London. You can imagine yourself in London. You've never been there, but you see a movie or you just imagine it yourself, and then you train yourself to do the right things. Like athletes do that. They imagine settings and then they train themselves, and it works. And of course, we use imagination a lot. An example of that is, most of us have not died in a car accident, but we can imagine what would happen. And through that, we are training ourselves to behave properly on the road to avoid those catastrophic situations. So there are lots of ways that system two is helping to train system one.
I have a question about system one and system two. So
yeah,
the large language models are doing reasonable job at solving reasoning problems. For example, they can solve math word problems and provide an explanation how they arrived at the answer.
Yeah.
So do you think those are system two problems being solved in a system by system one, or what's happening?
Yes, exactly. The reason they're able to kind of do a reasonable job on this system two tasks using system one machinery is because they've been trained on so much data, and they're big enough to capture a lot of knowledge. Remember, in what I've been saying, ultimately you can do everything with system one. I mean, except when you face new situations, and that these language models fail when they're confronted with some sort of system two task that's very different from what they are used to. So they're like clear reasoning failures that happen with those systems. If you were to include data that they train on that's like that, then they will be solving that problem. So that's why we need to have these two systems. The example I just gave about driving in London is a good example. But also, we don't want to have to retrain them with data of a particular kind each time we face these new settings. So we would like to be able to say on the fly. So we have the prompting mechanism in these large language models, but it goes in that direction, but it's not quite there yet. Where on the fly we could bring in new instructions that are very different from what they've seen before, and they should be able to incorporate that. But yeah, I think that these large language models, what they're saying is, so long as you stay within the same distribution, you can generalize in a very powerful way with system one. System one is very powerful, but if you want this fast adaptation to new tasks, if you want to be able to reason in this more sort of sharp way that humans are able to do and adapt quickly to these new tasks, you want system two. And like humans have it. I think it would be crazy not to try to design that into our machine learning systems.
Thank you.
Yoshua, this is Manik. Excuse me. I have lots of technical questions, but because we had so many of those, probably I'll sacrifice that for a non-technical question if you don't mind. I think there are lots of people who are just starting out their research careers in the audience, right? There'll be people who are thinking of going in for PhDs or young PhD students or people who are just starting their research careers in industry. What advice would you give for them about how they should go around about doing their research, right? Like if one day they should aspire to win the Turing Award, what should they do? And particularly if you have like specific thoughts about quality versus scale, taking risks and so on, or general advice, like what would you tell them?
Right. Well, many things. So first of all, don't think about the Turing Award. Don't think about awards. Don't think about recognition. Think about understanding what you're doing. Think about asking the why questions all the time. By the way, that's like the causal mind. That's like to figure out why is it like this. This is how you're gonna really make progress. As to like risk taking, well, that's a tough one. We are in a world where you have to manage your risk properly. So it's kind of sad right now. I see grad students, like PhD students, that are avoiding to take like more ambitious goals because they want to make sure to publish and publish enough papers in, in the best places. And the result of that, I think we all lose, because there's not enough risk taking going on. So we do incremental work. That's some variational stuff that exists. And that's useful work, but the big breakthroughs, the Turing Awards, but don't think about it that way, more like the big advances in science and understanding of how the world works come because some people at least are willing to take risks and try very new things. The reason that Jan, Jeff, and I got the Turing Award is basically because we stuck to our vision for a long time. Now, we were not grad students, we were professors, so it's easier. As you go, if you take an academic career, the more you advance, the more security you have. After you have tenure, you can basically, you can take a lot of risks. Unfortunately, that's not what typically happens. People who were not taking risks when they were PhD students typically were not going to take risks when they're going to have tenure. So what I tell my students is to hedge their bets. So in the 3 to 5 years of a PhD, you can explore multiple paths, and my grad students typically are involved in more than one project at a time. Often they collaborate with other students on other projects. They might not be leading that project, so they end up having a lot of papers. But also it hedges their bets. So they can have one project that's very risky, but they don't put all their eggs in it. They might have other projects where it's more incremental, and that's okay. Like we also need that stuff. So you can do that sort of distributed kind of decision making.
Right. Thanks. And also, do you have any advice on quality versus scale? Should they be looking to publish, let's say, 1 or 2 or 3 great papers in their PhD, or publish lots and lots of papers?
Well, it's kind of the same as the risk aspect, right? So, like ideally, we would be in a society which rewards risk takers, even if they fail. Unfortunately, it's not exactly where we are right now. Academia should be the place for that, where you can take risks and go for quality, period. And so the answer I'm going to give is the same. So, for your own sake, you want to take a good mix of these higher quality, papers that take a longer time to write and figure out, and maybe sort of bite-sized smaller pieces. Now, there's something interesting though about publishing, which is I favor small papers in which is what we have in computer science with our conferences, for the following reason. I mean, in general, okay, so I also sometimes write long papers, but But most of the time, it's easier to digest a paper that has a single message, single contribution, not 6 contributions. That's like, there should be like one really clear message, one new idea that you have validated. And so, you know, it's not a good idea in general, unless you build something like very, like the foundations of a new field or something. But in general, you want to have, you know, if you have multiple ideas, when you build a system that does something, to break it down into pieces that are each have value and can be generalizable in other settings and can have a single clear contribution that can go into one paper. So that's another piece of advice that's related to your question.
I have another question. So you have worked on applications of machine learning to climate change. Could you speak a bit about
that? I continue to that. Yes.
So how can ML help climate change? What can we do for it? Right.
So my colleagues and I wrote this paper a couple of years ago, which surveys the many ways in which machine learning can be used to help fight climate change and even help adaptation. Unfortunately, there is no silver bullet. So there's not like one technique that we can go and one problem that we could work on and it would kind of solve everything. That's the sort of thing I'm interested in. Like I want to go for the most risky but highest reward project that I can find. But there are many sort of things, projects that could help, you know, reduce by 1% here, 1% there, 3% there. Now, what I'm currently working on with respect to climate change. So we have a project where we've been working on the visualization of climate change. So, you know, I feel like a lot of the problems we have with climate change is not that we don't have the technology, it's that we don't have the minds to do the right things. We are like, there are cognitive biases, there's politics. So collectively, we're not taking the right decisions. And so that we designed a website with a kind of GAN that generates images of your house flooded. And so hopefully this kind of tool can help people, and we have studies now showing that they help people become more, put more priority on, you know, what to do about climate change. So that's one kind of project. Another project that I'm working on is new material discovery. So, you know, things like batteries, carbon capture, it's chemistry and physics. And actually the kinds of tools that I've been talking about today, like GFlowNets, can be used in active learning to explore the space of materials, the space of molecules that can be used in those tasks. And you know, the potential, if we found a chemical process that can do carbon capture efficiently and cheaply, it could be a complete game changer for fighting climate change. So that's the sort of thing I'm doing, but there's like lots and lots of opportunities. You can check that climate change and AI paper. There's an organization that has been behind that paper and is working in connecting machine learning people interested in climate with climate scientists, with all kinds of applied domains where machine learning can be used to help fight climate change. It's called Climate Change and AI. You can check the website.
Thank you.
Any other questions? Rajiv, any last thoughts from you?
Nothing else. I think we're almost.
We're at the time.
Yeah, I'm sorry, my internet connection dropped off for a while, so I lost the last bit of your answer. But thanks, Yoshua, so much, not only for a fascinating talk, but also a really stimulating Q&A session. So it was a pleasure having you, and thank you so much.
My pleasure. Thanks for organizing this event. Bye-bye.
Thank you, guys. Bye-bye.